Hi viewers, welcome to the series of lectures where we were looking at different problems that were asked in GATE. So here in this particular video I'm planning to solve three problems. The first two are relatively easy. The first one is shown over here. This is the first question and this is the second one. Going ahead with the first question, in this particular question they are asking the natural frequency of the spring mass system shown in the figure. In this particular figure, these two masses are arranged in series or parallel. Series or parallel. The key thing you should observe is that for this particular configuration, whatever be the extension that is felt by the first spring, the spring with a stiffness of 4000 Newton per meter, the same deflection will be felt by the second spring as well, which is having a stiffness of 1600 Newton per meter. So effectively that means these two springs are in other words, these two springs are connected together in parallel configuration. That means the net stiffness can be written as K nu equal to K1 plus K2. That will be 5600 Newton per meter. Or rather than calling it the new stiffness, I would call it the effective stiffness. So this is the effective stiffness in the system. Or in other words, you can also think in another way. Let's say what will be the stiffness offered by the system if I am moving this by, let's say, unit length dimension, that is a meter or an mm. Then there are two resisting forces. This will resist because this spring is getting compressed, so this spring will push here. Similarly, this spring is getting extended, so this will try to bring this particular mass or pull this particular mass towards this side. So the two forces coming from the springs are acting in the same direction, so the net stiffness in the system can be thought of as a summation of the individual stiffnesses. Make sense? Okay, now the rest is just plug and check, because you know omega n, where units is radians per second, is given by root k by m. That will be 5600 divided by 1.4. But remember, they are asking the answer in hertz. So what you should do? So omega n in hertz is given by 1 by 2 pi root k by m. Just plug in the values and get the answer. If you work out the numbers on your own, then you will get the answer where natural frequency will be near 10 hertz. So the answer is option B. Now let's go ahead and try to solve the problem 2. The problem 2, you have a arrangement of springs, and again in that particular problem as well, you are asked to compute the natural frequency. The one thing we should do before we compute the natural frequency of the system is that we should compute what is the net stiffness in the system. So here you can see there are two springs, they are connected in parallel, and we have another spring which is connected in series with this. So similar to what we have learned in electrical circuits, I'm planning to replace this particular spring system with two springs initially. So this is the first configuration. where I have two springs, and this particular spring is a substitute or a replacement for the two springs that we can see over here, which essentially means that this single spring should have the net effective stiffness of these two springs. These two springs are connected in parallel. That means the net stiffness of offered by these two springs will be the sum. That will be K. And this particular spring will be same as that of this. So it will again have a stiffness of K. Now see, we have two springs now. We have two springs as shown over here. Now what is the net stiffness offered by this particular arrangement of springs? For that again we need to compute, or we need to appreciate what is the kind of arrangement or of these springs. These are connected in series, so we have K and K connected in series, or in other words I can say K and K by 1 connected in series, which implies the net stiffness will be K by 2. So that means I can replace this with one spring and a mass system, where the one spring is having a stiffness of K by 2. Now if you want to compute the natural frequency, it is root K by M, K effective by M I would say, and the K effective is K by 2M. So option A is the answer, or the natural frequency is K divided by 2M. Always remember that the units are radians per second, not hertz. We have another interesting problem over here. See, here there are two springs once again, and they are placed on an inclined table as shown here, and the question is, what is the natural frequency of the system? See, I will first explain the crude way to answer the problem and then get into the more formal way of solving this particular problem. So, generally for a single degree of freedom, this is the differential equation that we are planning to solve for a single degree of freedom undamped system, and the natural frequency is computed like this: omega n equal to root of K over M, or K by M. See, thus K denotes the net stiffness into the system. So here you can observe the way how which this particular system is going to vibrate will be like this. The mass will move over here and then it will go over there. So that's the way how this particular system is going to vibrate. Given that, what will be the stiffness, or what will be the force that will resist that sort of a motion? If there is any force that resists that particular motion, then they have to come from these two springs. And one more thing, let's see, if this particular mass is moving over here, K2 will resist that particular motion in the upward direction, and on the other hand K1 also resists that motion by exerting a pull load on this mass in the upward direction. So those two spring forces are acting in the same direction, and moreover none of the options have values which are expressed in terms of theta. So theta is an independent quantity. I'm just telling a crude way to solve the problem, so you can get, or you can assure that the effect of theta is not that relevant. And I have already told you the spring forces act in the same direction, so the net stiffness in the system will be the summation of the individual stiffnesses, that is k1 plus k2, and the natural frequency will be given by omega n equal to root of k1 plus k2 by m. And the answer is D. This is a crude way of answering the problem. Now let's get into the formal way of answering the problem. The formal way of answering is first understand what is the static deflection scenario for this particular problem. So the static deflection scenario will be something of this sort. Initially, this is the configuration, the springs are unstretched. Okay, the moment you leave it, the spring K2 will get compressed and the spring K1 will get extended because there is gravity acting on the system. And let's say the static deflection is delta. Okay, now from the basic principles of engineering mechanics, I can evaluate the static deflection delta in terms of the system parameters, which are K1, little m and K2, and obviously theta. So let's go ahead and do that. So for that particular thing, we need to draw the free body diagram as shown over here. So here I have shown all the forces acting on the particular mass little m. This is the mass little m, and I have summed the forces along this particular direction, along the direction of the sliding. And here you can see it is acted upon by three forces. One is the gravity force, mg sine theta, which is acting towards this direction. And then there is K1 delta, the spring from the force from the first spring, pulling it up, and the force from spring 2, which is pushing this particular mass upwards again. And this is the static deflection condition. So mx double dot is equal to 0, or there is no acceleration. So if I add all the forces, then I should get 0. So I have done it here. So I have added the forces in their algebraic sense. Then I am arriving at this particular expression, mg sine theta equal to k1 plus k2 into delta. So now I have an expression for static deflection in terms of all the non-parameters. That's not over. Now we need to define a coordinate system x, which is from the static deflection condition, or it should be defined from the point of static deflection as shown over here. So it is defined like this. So this is the origin and this is the positive direction of x. And this was the initial configuration. This is the static deflection configuration. And now let's say the mass gets moved by an amount little x from its static deflection position. Okay, and say at this point of time, or at this particular instant, the whole mass is having an acceleration of mx double dot along the sliding direction. Clear? That's how you arrive at the governing equation of a particular discrete mechanical system. So again, I'm drawing the free body diagram over here. Now this particular mass is accelerating with an acceleration of x double dot because it is vibrating. In the earlier case it was static deflection. Here it is vibrating, and if I put all the forces acting on this particular mass little m, there is a first spring will pull this thing up now, but with a different force. I have both static deflection and the new extra term, which is little x, because the spring is getting extended by an amount equal to delta plus x. Delta because of the static deflection and x is because of the vibration. And gravity is still acting there, and then you have k2 times delta plus x. These are the different forces acting on the system, and this whole thing is moving with an acceleration of mx double dot. Now if I again sum up all the forces in their algebraic sense, then I will end up here. Mx double dot is equal to mg sine theta minus k2 into delta plus x minus k1 into delta plus x. These two forces are given a negative signs because they are opposing the motion. And once I rearrange the terms, I get something of this sort. And From the first equation or from the condition of static deflection, I know that mg sine theta should be equal to k1 plus k2 into delta. So these two terms are the same, like 2 minus 2. So these two cancels out and I'm only left with this particular term over here. That means the differential equation that governs the motion of this particular system is this, which in turn means that natural frequency of the system is root of k1 plus k2 by m. So this is the answer. You can do all this maths and get into the final answer. Otherwise, you can use a bit of your logic or intuition and get the answer. I will suggest you to do the latter way because it assures you your 2 marks. The other one can get wrong if you are not sure of the concepts. So shortcuts are meant only if you have good grip over the fundamental concepts of vibration. Thanks for watching.